Okay, so hey everyone, today I'll be making the week 6 physics quiz video. So first we start with the first question. Which of the following actions would demagnetize a magnet? Okay, so first of all, using an alternating current on on an electromagnet. Okay, this one you memorize. I can't really explain because we didn't take the AC, which is the alternating current yet. When we do, they probably repeat this, they recap it, and at that point I'll go further into it. Okay, dropping a magnet and storing a magnet without a soft iron keeper. Now, dropping a magnet, I feel like it's common sense. Storing a magnet as a soft iron keeper. My trick for memorizing this is it's in the name keeper. It keeps it magnetized. So without it, it would lose its magnetism. So that's the first question. There are more actions, by the way. I'll list them at the end of the video. Now, the term magnetic field describes the property of the space around the magnet. It's in the name field. Field means space around something. Magnetic magnet. So the space around the magnet. Now, the plotting compass. Okay, this is how you know it. So the field is pointing rightwards. So and this is near the poles. So this would be the opposite of where the actual field outside of the poles is going. Let me show what I mean. I'll show you what I mean in more detail in another question. So for example, this would be my magnet and S, right? It would go like this. So I extended the line too long. It would go like this. Okay, I mean it's a very bad drawing, but you know, I'm not the best artist. So it's like this. Now, as you can see, it is pointing rightwards at this time. Look, it curves to the right, which is why it goes right. You know, this is. I'll show it. I mean, again in another question, where it's going to be way more clear and it's going to be way more understanding. But for now, uh, just know that if it's going to be pointing rightwards because this is the plotting compass. It plots the magnetic field. Okay, question 3. What are the two poles of a magnet? North and south, obviously. And the extremity pointing north is the north pole, and the one that's pointing south is the south pole. It's in the name. Okay, this one I just answered. Whatever. Which of the following statements are true about the current meter? The magnetic field is in a plane symmetric radial field. In a construction of a current meter, a U-shaped magnet with concave pole faces is used, and the magnetic field in a current meter can exert a sideways tangential push on a current carrying wire in the annular gap. Okay, now this one's pure memorization. I don't really think I can explain anything. Just know that in a current meter, you're gonna have plane symmetric radial field and not axially symmetric. This is wrong. This is correct for the current meter. I think the axially symmetric one is for the loudspeaker. I'm not sure. They probably will. So there is another thing. You have to check the book for this one, but whatever it is, it's that. So plane symmetric radial field. This you memorize for the current meter. Okay. The construction of a current meter U-shaped magnet with concave pole faces is used, and my trick for memorizing this one, you see current carrying wire, it's going to be current meter, current, it's going to be there. And if they don't show that, you just can memorize it by sideways tangential and annular gap. Yani that's 3 ways to memorize one question or one part of a question. If you see U-shaped magnet with concave pole faces, it's going to be a current meter. And if you see plane symmetric, it's gonna be you know, it's gonna be current meter. Okay, moving on. Let me just erase this thing. My prediction for these types of questions, by the way, it's gonna be matching between the current meter and the speaker. I'm not sure though. We'll see when we get to the exam. Okay, this is a very easy question. North repels north and the south repels the south, so this is gonna be repulsion. Okay. Now, south repels or south attracts the north and the north attracts the south. This is going to be attraction. And the north attracts the south and the south is going to attract the north. So it's going to be attraction. Basically, all you have to know, and I'm sure you already know this because there's no way you're in grade 10 not knowing it. Opposite poles attract, like poles repel. Am I recording my audio? Yes, I am. That's nice. Okay. Question 6. Difficult to magnetize in the first place is a hard magnet. You can see difficult, hard. Like they both mean the same thing. Soft iron, soft is in the name, so soft is there. Permanent magnets and compass needles is gonna be hard magnet, and the hard steel hard is in the name, so it's gonna be hard to it's gonna be hard magnetic, easy to magnetize, but rarely uses magnetism. It is soft. Now, my trick for this is soft magnets are very easy to magnetize, right? They're extremely easy to magnetize. It's called I forgot what the phenomenon is called. It's in the induction. That's what it's called. When you when you induce, or I don't know what it's called when the verb of doing it is an induction though. It is there's different types of like difficulty on how to do it. The soft magnets are really easy to magnetize. All you do is place the magnet near the material, and it became a magnet. However, hard that is a soft magnet that loses its magnetism really easy. Just how easy it was to magnetize, it is that much easy. That isn't really the most grammatical sentence, but whatever. It is that easy to lose its magnet. So if it's easy to magnetize, it's easy to lose its magnetism. And if it's hard to magnetize, it's gonna be really difficult to lose its magnetism. And this is why hard magnets are considered, or hard magnetic materials are considered permanent magnets. Okay, question 7. Select the rods that can be magnetized by stoking them with a magnet. It's going to be nickel and steel. I don't feel like I have to explain this. It's going to be really easy. Question 8. When a magnet attracts an object made of ferromagnetic material, the latter behaves like a magnet. This phenomenon is called magnetic induction. This is what I was talking about. Okay. So what I mean when I say magnetic induction, basically a magnet. So let's say this magnet, right? As what did I open? What is a distance learning video? Okay. I just put in random answers for half of my questions. So which question was I on? Okay, here. I was after this. After this. After this. I think here. Yeah, after this one. Okay. Yeah. After this one. There we go. Question 8. Okay. So S and N. Right? Let's say this is ferromagnetic material. Ferromagnetic material means it can be attracted and attracted to a magnet, and it can be magnetized. So I'll just say Fm for ferromagnetic. When this comes near it, it's going to be attracted, right? And then this behaves like a magnet. On the time that it is like connected to the magnet, as soon as it like loses its connection, it's not going to be magnetized anymore. This is magnetic induction for soft materials. If it's hard, it's going to be much harder to magnetize. But when it does, even when you disconnect the magnet, think of it as like a middleman between two things. So say this is like another material that can be connected to a magnet. So an S here, this is let's say this was hard magnetic material that was already magnetized. It still behaves like a magnet, and it still acts like one. It is used as a permanent magnet. خلاص, it's permanent. However, if it's soft, so I swap this H with an S. Okay, this no longer magnetizes. The only condition for soft, it is very easy to magnetize, but it's very easy to lose its magnetism. Hard is very hard to magnetize, but it's very hard to lose its magnetism. It's there, hard. Easy, soft. Okay. Consider a permanent magnet with 4 points A, B, C, and D shown around it, as shown below. This is the question that I was telling you about, the one that goes into the magnetic plotting compasses in detail. So let's start with the A. So first we draw our magnetic poles, right? It's gonna go like this. The arrows go this way because it's from always gonna be from N to S. Keep this in mind because they will ask you later what is the magnetic field of a simple bar magnet. Okay. Now this is all we need for this question. So at point A, this is gonna be my left. I don't know if it's gonna be different for you, but it's probably not gonna be. But if you don't know your left and right, this is left, this is right. Uh, so the magnetic field at A is directed leftwards because as you can see, it's going this way. A is going this way with the magnetic field, so it's gonna be leftwards, right? The magnetic field at B is directed rightwards because as you can see here, it goes right for a bit, then it goes to the left. But at the point where it is at B, it's going rightwards. Okay. Now uh, C is directed leftwards, as you can see, because it's going to the left, and D, it's going in at D and into the S, and that inside direction is going right. So A is leftwards, B is rightwards, C is leftwards, and D is rightwards. Question 10. Rank the magnitude of the magnetic field at different points around these magnets. label the point where the field is strongest 1. Okay, now obviously you know it is from N to S, so it's going to be strongest at, or let's make it pass through C, you know, for our convenience. So I'm just going to draw one line that passes through everything, and if I can draw like this, okay, something similar, whatever, not very accurate, but you know, the best I can do with a small picture. Now here, and I must mention this is gonna be the line at N to S in the other bar magnet, whatever. But the interesting part about this is at S it goes up. This here, let's not make it pass through A. Actually, that's not a good idea. At when it's two S's, it's gonna go like this. It's gonna not attract each other. These two lines are gonna be parallel. It's not parallel right now, but this here is called the neutral zone since these two repel each other, right? And or these arrows are this way, okay? And it's gonna go like this. You know that the lines of a bar magnet. I'm not gonna draw them. Anyway, like this we can rank now. Okay, it's going from N to S. So N is gonna be the strongest point. So B is 1, right? A has no point. A is not magnetic at all. A is neutral. There is no magnetic field around A. So it's gonna be last 4. Right? C isn't at S quite yet. And C is it's, by the way, just because it's at S doesn't mean that it's the weakest. At the poles, in fact, it's the strongest. Anyway, in between is gonna get weaker. So here it's not quite at the pole, and it's not quite at any of the poles. It's kind of in the middle there, but it's relatively close to the magnet. So C is gonna be 2, right? D isn't at the neutral zone, but however, like if you still draw it, if you extend this line, you can see it's gonna pass through, right? You can see it passes through. So D is 3, and it doesn't. A again doesn't pass through anything. No line, no magnetic field lines pass through it. So A is last. So it's gonna be 4, 1, 2, 3. Okay. Question 11. Give the expression that relates the current I that came last week. It is going to be V equals IR. That is I over R. V equals IR or V equals RI, as they said. It could also be I equals to V over R. It could also be R equals to V over I. Whatever. There's 4 answers. So 1, 2, 3, 4. Okay. Give me a second. I'm just going to pause the recording for a bit. Okay. So I answered this one. Now question 12. Oops, my pen fell. Okay, this is very easy. Resistance in a series circuit is additive. So R1, R2, R3. This is going to be 4 plus 5 plus 6, which equals to 9 plus 6, which is equal to 15. This is very easy. Question 16 or 13, sorry, I don't know where I got 16 from. So in the diagram below, blah blah, resistance is this, is that. Okay, so let's just write it. R1 is 20 ohms, R2 is 30 ohms. Okay, now the resistance is going to be 1 over R equivalent resistance يعني is going to be 1 over R1 plus 1 over R2. Now 1 over RE is equal to 1 over 20 plus 1 over 30. This equals to, you have to make these a common factor. This is going to equal to 1 over 12 in simplest form. So then you flip this. So you flip this. So RE equals to 12 ohms. Okay. Question 14. Which of the statements are true about field lines? They never cross. Okay, they never absolutely cross. I mean, and you're drawing now. If you have a small picture, no one's gonna check if it's computer, but anyway, you can make them cross. It's fine. Only one resultant field can be present at each point. So that means, yani, I can't have two fields like this. Heck, it's not possible. Okay, and if extrapolated magnetic field lines do not meet at the poles, extrapolated basically means like I don't really know what extrapolated means, but how to explain it. بس يعني just give me a second to look up the official Google definition. Okay, so it basically just means to extend. Yeah, if you extend them, they're not going to meet at the points. I mean, I thought it was extended, but I don't know why they make it fancy. It means if you extend it, they don't meet at the poles, which isn't wrong because if you extend the field line, it's not going to meet. Iron fillings are sprinkled next to a bar magnet. This was in like the grade 6 science book, and I remember it very clearly. Where the iron fillings are packed close together, the field is strong. So this means like you have a bar magnet here, right? Whatever, I'm not going to draw S, and these are the iron fillings. Okay, they're very close to each other here, right near the pores, especially near the pores, they're going to be very close, like this. However, if you're like far, they're going to be like spread apart, right? You notice how they were close, like here and here. Here, they're like very spread apart. This is what they mean. Basically, the more distance there is between the like the poles and the actual magnet itself, uh, or like the distance increases, it's gonna be like less fittings, and it's gonna be weaker, and there's gonna be more space between them. Okay, now which of the following shows the correct flux pattern? Okay, now obviously this says that it's going from S to N, which is wrong. It doesn't go from S to N. This says it's going from S and it's going from N, which doesn't make sense. Look at the directions of the arrows. This is leaving from S, which is automatically wrong. Okay, this one says it's going from N to S. This part, the first part is right. However, if you notice, the arrows are moving this way, which doesn't make sense because we said that the arrows are going this way. So this is the actual field line. Now, how does it make sense that the line is going this way? It doesn't. It's wrong. As you can see, the lines, the arrows are going to the left. Meanwhile, they should be going to the right. So this is wrong. Okay, which leaves option 4, which is correct if you think about it, because it looks like it's leaving from the north and it's going to the right. The way it aligns with the North Pole is correct, and it enters through the south, which is correct. Okay, so 4 is our answer. Okay, question 17. This is gonna be equal. This is an application of. Sorry, I don't know what that was. V equals IR. They want I, so I is equal to V over R. The V is 5 and the R is 40. So this is gonna be I is equal to 5 over 40. You do this on a calculator, you get 0.125. However, this is gonna be in amperes because listen, you're dividing by SI unit and SI unit, you're gonna get the SI unit. Like the unit, like without a suffix. For example, you're not dividing kilovolts or megavolts, right? You're only dividing by volts. By the resistance, by the ohm, the normal ohm. You're not dividing by kilo ohm or milli ohm. No, nothing. Right? You're dividing purely on by the units. So this is going to give you the pure unit, which is A, which is the ampere. However, in the answer, they want milliampere. So you multiply by 10 to the power of 3, which means you just shift the decimal place 3 times. So 1, 2, 3, which is 125 milliamperes. Okay. Question 18. A small iron needle is the plotting compass that's used to determine the magnetic field. We said it's an iron compass. Another way that magnetic fields add as vectors is to say that the fields obey the principle of superposition. Superposition means you can add vectors. Basically, that's what that means, as far as I'm aware. The direction of the magnetic field is the direction of the force it produces on a north pole placed at that point. If you think about plot it, right, like draw the magnet as N. Look, it's going from the north, and there's a force here. There's obviously going to be a magnetic force. So this is the force that is being produced on the North Pole. This is just the direction of the magnetic field. Now, there is a formula. You don't need to memorize it. F equals to QB, something like, or BQ. I don't remember. I don't need to note, and it's used to show if it's used for another question that is going to be seen hopefully now. Now, the direction of the force by the magnets directed rightwards. Okay, because if you think about it, extend it here like this. See, it goes to the right first, then eventually it curves to the left. Okay. The direction of the force is directwards. We said this, and here you notice that they're gonna repel, so it's gonna go like this. Right? Here is a neutral point. There is no force. Nothing is being applied here. X on anything that's being applied here. There's nothing. This is the neutral point, which means there's zero magnetic force. So the net force is gonna be 0. Okay, and let me just go back to you and to show you why. If you think about it from the physical like standpoint, not from the magnetic, this is gonna repel this, right? And they're gonna repel with equal force. Let's say 5 newtons here, 5 newtons here. Now this is gonna cancel out with this because this is in opposite direction. So this cancels out with this, which leaves 0 in the middle. Okay, question 20, and we're almost done with the quiz. Just 3 questions left. Uh, induced poles. Now, obviously, look, you can see here they're attracted, right? They're not repelled from each other, which means that these 2 poles are opposite. So Sn and S here, and the other opposite pole at the bottom as well. Basically, because if you don't understand, they're attracting, right? Here there is no space, which means they're not repelling each other, which means they're attracting on both sides. So you put opposite poles since opposite poles attract. Okay, the gray bars are called keepers. They are usually made out of soft iron. We explained why, this is how you store a magnet, basically. Okay, this doesn't need that much attention. It's actually very easy. Now, plotting compass, we said it at the start, it's made of hard magnetic material. It's made of, so it's a permanent magnet. Speaker coil and loudspeaker, it's made of soft magnetic material. And the refrigerator, common sense, why it is made of a hard magnetic material. So I don't really need to explain it. Magnetic keepers are soft because we said it's made out of soft iron. Okay, question 22. This is the one I'm talking about, right? So, this obeys the forces chapter we took last year. So the resultant force, these are going to be parallel forces. I'm not going to draw it, but it's going to make a right triangle. And it's going to be parallel forces. So R, which is the resultant, is equal to, it's basically the hypotenuse. So this is going to be our resultant force. Here. This is R. Okay, I'm not going to go into detail because you don't need to. It's a right triangle. That's all you need to know. So it obeys Pythagorean theorem. So this is going to be 3 squared plus 4 squared, which equals root 9 plus 16, which equals to radical 25, which equals to 5 newtons. So the resultant force is 5 newtons. Now, what you do the tangent to find the direction, because remember, this is going to be the angle of the resultant between the other forces here. This is theta. So tangent of theta is equal to the opposite, which is going to be he, which is going to be, let me just get my calculator. Give me a second, because I need it. Okay, so let's solve this. So for this one, right, what you're going to do, my calculator is with me. First, I would recommend plotting it because I'm in a hurry. I want, but still, it's fine. Let's do it. So this is our forces right here. Or do you want to make it better? It goes north, then it goes east. So like this. The angle is going to be here, theta. So it says it exerts 3 to the north, so it's going to be 3 here, and then 4 east. 4 is here. Okay, so this is our resultant. This is a 90 triangle, as you can see. We're going to have to apply the tangent. What else gives the opposite and the adjacent? So tan theta, I already wrote it here, equals to 3 over 4, meaning that theta equals to tangent inverse 3 over 4, which equals to 37 degrees, approximately, to 2 significant figures. Okay, so we know it's 37 degrees, right? Now, what are we going to do with this info? You can see that it goes to the east, right? It goes to the east here, which means that it's going to go east 37 degrees north, because it started at the North Pole. It goes north of that, and then it goes east. My bad, give me a minute. So then this means that theta is 37 degrees east, right? Starting from the north. So I don't know why I put that east degrees here. Okay, now the south pole is going to be the opposite. It's simply logic. So it's going to be west, or sorry, I flipped it entire. Yeah, I flipped it. It's east and now the thing is going to be on the south pole. If P is the south pole, it's going to be the opposite. Simply just flip it. West, 37 degrees, south. That's it. It's the opposite. It's just opposites. Done. So, question 23, correct answer here. So, yalla. This you memorize the north armature and the south armature. And what can be said about the magnetic field in the loudspeaker? It is actually symmetric. As I said, in the loudspeaker, it's actually symmetric. In the current meter, it is gonna be plane symmetric or plane, yeah, plane symmetric radial. Again, just memorize them. And this is the end of the quiz. Okay, thank you guys for watching. Good luck. Yalla, bye. If it, inshallah, starts properly.